Good morning. I am Roberto Fusco from Eni Research Center for Renewable Energy and Environment. I will speak about the exploitation of solar energy using photovoltaic devices. Man and all that surrounds him consist of two main components, matter and energy. Although they may seem like two familiar concepts, their precise definition is more elusive than expected. Our bodies, animals, plants, the earth, and everything around us is made of matter. The bodies are characterized by possessing a mass. Energy is a concept more intangible. Light and heat are forms of energy, but there are others such as the mechanical energy, electric energy, and so on. One possible definition of energy is the ability of a system to do a work. Men, like animals, plants, and all living organisms, need energy to think, study, move, work, and do anything. In general, to live. Energy and matter are the constituents of the universe and can be transformed into one another through the famous Einstein relations E equal mc square, as occurs in nuclear reactions and in the stars. Man draws energy from the food it eats, consisting of animals and plants. Animals in turn feed on the other animals and plants. The plants get their energy from light. Even cars, computers, TV sets, radios we use daily need energy to operate. The main source of direct and indirect energy of the Earth is the Sun, the star closest to us. As you can see from this slide, the amount of energy that the Earth receives from the Sun is in just 1 year is about 40,000 times that consumed by humans in the same period. So there are good reasons that lead us to understand how to exploit this immense source of energy without contributing further to Earth pollution. The energy that comes from the Sun is not evenly distributed on Earth. As you can see from this map, some regions around the equatorial areas receive on average 3 times more energy than polar areas. Obviously, in the most heavily irradiated areas, there are more opportunities to exploit this energy. Energy can be converted from one form to another, and this seminar will focus on just one of these transformations, light to electricity. We know that plants are able to transform solar energy into chemical energy necessary for their growth through a sophisticated photochemical process called photosynthesis. The overall efficiency of this process is, however, limited to about 1%. In the last decades, man has succeeded in developing some devices called solar or photovoltaic cells, able to transform solar energy into electricity. With a more efficient process, spanning from 15% of common photovoltaic panels to over 40% of triple and quadruple junction cells in concentration systems. We will now try to understand what is a solar cell and how it works. Many of you have had the opportunity to observe the solar panels on the roof of houses or small panels used to recharge batteries or mobile phones. They are made from bluish material on which are placed some metal contacts connected with electric cables. When these solar cells are illuminated, they convert light into electrical energy that can be exploited as you like. We go beyond their outward appearance to understand how they are made up and how they work. The structure of a photovoltaic cell is more complex than would appear from outside. The cell is composed of various superimposed layers. At the bottom of a protective glass, we find a grid of electrical contacts which represent the negative pole of the cell. The bluish underlying material is mono or polycrystalline modified silicon. It is the so-called N-doped silicon. Below, we find a further layer of P-doped silicon, and finally a further metal electrode, which is the positive pole of the cell. The outer wires are connected to the two electrodes and allow the passage of electric current in the external circuit. The heart of the device is the interface between the two layers of P and N silicon, the so-called P-N junction. When the light hits the cell, passing through the holes of the upper grid, at the P-N interface, pairs of negative and positive charges are generated. They migrate to opposite directions toward the two electrodes. Negative charges are collected by the upper electrode and flow through the external electric cable towards the positive pole, where recombines with positive charge, creating an electrical current. What is the origin of these electric charges? What does it mean, P and N semiconductor? To answer these questions, we need to know a little more of the matter and its electrical properties. Silicon is a so-called semiconductor material widely used in the realization of transistors and integrated circuits utilized in all electronic devices we use every day. Solid materials can be divided into three major categories related to their electrical properties. Conductive materials, such metals like copper, gold, silver, that are able of conducting electricity. Insulating materials like glass and plastics. Semiconductor materials as silicon, which are poor conductors but became able to conduct electric current in particular conditions. To understand what distinguishes a conductive material from an insulator, we must know a little more about their elementary constituents, atoms. That matter is made of atoms has been speculated since the days of ancient Greece. However, to find the first evidence of the existence of atoms, we must go back to the 18th and 11th, mainly thanks to the contribution of chemists. Later, the concept was accepted also by physicists across the 19th and the 20th century. Physicists discovered that atoms were anything but indivisible particles, as suggested by the Greek etymology of their name. But in turn, they are made up of more elementary parts, the nuclei, electrically positively charged, and electrons, negatively charged particles. The nuclei, placed at the center of the atomic structure, consist of positively charged particles, the protons, and neutral particles, the neutrons. The electrons are negative particles that occupy outer shells. The real nature and the stability of the atomic structure was an intriguing problem for physicists and occupied them for several decades. It is not possible here to do a complete exposition of the theory that describes the behavior of small particles such as electrons and protons. It is enough to know that their behaviors are dictated by the laws of quantum mechanics, requiring electrons to occupy only certain regions of space around the nuclei, called orbitals, characterized by discrete level of energy. In addition, each orbital can be occupied by no more than 2 electrons. The electrons are bound to the nuclei with a force that depends on their average distance from the nucleus. The electrostatic forces make charges of opposite sign, such electron and nuclei, attracting each other, while those with the same sign repel. The higher the force linking the electrons to the nucleus, the higher is the energy required to separate them from the nucleus. So this situation can be graphically represented in the form of energy levels. By convention, in this representation, 0 is the value of the energy of a free electron placed at the infinite distance from the nucleus. The energy levels of the electrons, most strongly bound to the nuclei, are those represented in the lower part of the diagram and require more energy to be detached. They occupy more negative energy level. The electrons, less strongly bound to nuclei, occupy the levels with the less negative energy. This latter can be more easily detached. Atoms with different electronics configurations represent the chemical elements listed in the periodic table. They are distinguished by the atomic number, representing the number of protons in the nucleus perfectly balanced by the same number of electrons. The electrons occupying the outer orbitals are called valence electrons. They are particularly important because allow atoms to bind each other, forming molecules and materials. I want to remark some atoms placed in the middle of the periodic table because they will play a key role in the structure of a solar cell. They are silicon with 4 valence electrons, and atoms placed on the left and the right columns having respectively 3 and 5 valence electrons. The chemical bond in molecules and solids is an important topic that we will discuss now. Materials are made up of extended set of atoms linked by so-called chemical bonds that are constituted by electrons shared among 2 or more atoms. Only the outermost electrons, valence electrons, participate in the formation of chemical bonds. When 2 or more atoms are close enough, they can exchange their valence electrons. The highest energy levels are no longer confined on individual atoms, but extend between 2 or more atoms as in solids. Now it is important to point out that while in an isolated atom there are only the electrons belonging to that atom, and their energy levels are distinct from each other, in solids consisting of many atoms, the number of electrons is so large that their energy levels became almost indistinguishable from each other. They can be grouped into sets of levels said energy bands. Because the electric current is constituted by a flow of electrons, a conductive material, to be such, must be constituted of atoms whose weakly bound outer electron can be easily detached to be involved in a flow of negative charges, acting as an electron gas. On the contrary, the insulating materials are formed by atoms in which the outer electrons are strongly bound and cannot give rise to a flow of charge. We have seen that to detach an electron from an atom requires an amount of energy to win the electrostatic force that binds the negatively charged electron to positively charged nuclei. We are now able to distinguish the insulating material from the conductors and semiconductors. In our graphical representation of energy bands, conductors can be represented by an energy band only partially filled by electrons. In this case, very little energy, for example provided by the heat environment, is required to blow many electrons to the empty energy levels, allowing them to move, giving up to electric current when an electric external field is applied. This situation occurs in metals. On the contrary, in insulating materials, the valence band is completely filled by electrons, and the conduction band is located at much higher level. The energy difference between the highest energy level and the valence of the valence band and the lowest energy level of the conduction band is called energy gap, or simply gap. A lot of energy is required to promote electrons from valence band to the conduction band, a situation that cannot occur under normal conditions. In semiconductors, the situation is intermediate. The energy distance between the valence band and the conduction band is significant, but not so high. In intrinsic semiconductors, such as silicon, at room temperature, only a few electrons can jump from the valence band to the conduction band, and they are poor conductors. To increase the number of electrons that can be promoted into the conduction band, semiconductors can be slightly modified through the so-called doping process. Starting from silicon, a semiconductor consisting solely of silicon atoms, it is possible to replace some silicon atoms with others of different nature. The silicon atoms have 4 valence electrons, shared with other 4 silicon atoms in the formation of chemical bonds. Each chemical bond is formed by 2 electrons. Replacing a silicon atom with an atom of boron, aluminium, gallium, or indium, having only 3 valence electrons, one of the 4 bonds with adjacent silicon atoms became incomplete. This situation creates a hole in the valence band and a new empty energy level just above the valence band is formed. An electron can easily jump into this energy level from the valence band, creating a further hole. This situation makes partially mobile the electrons in the valence band, increasing the conductivity of the material. Other trivalent atoms will create other holes. Such a semiconductor is said positively doped or p-doped because of the lack of some negatively charged electrons. The behavior of the holes is related to collective motion of the remaining electrons. The holes can be treated as positively charged particles. Replacing a silicon atom with one having 5 valence electrons like phosphorus or arsenic, the extra electron will occupy an intermediate energy level just below the conduction band. In this case, we talk about n-doping. This weakly bound extra electron can easily jump to the conduction band, increasing the conductivity of the material. So we have just defined P and N semiconductors. Now let's see what happens when a P semiconductor is placed in contact with an N semiconductor to create a so-called p-n junction. At the interface between the two materials, the electrons in the conduction band of the N semiconductor will migrate to occupy the partially filled levels of the P semiconductors. This electron-hole recombination allows to gain energy, stabilize the interface. This charge migration causes a polarization of the interface, and we will find an excess of negative charge on the side of the P semiconductor and an excess of positive charge on the side of N semiconductor. In this situation, energy levels in the pi semiconductor split up and down to those of the N semiconductor. Furthermore, the polarization causes a preferred direction for the electrons present in the conduction band from the N semiconductor toward the pi semiconductor. Such a device, based on a single p-n junction, is called diode. In a diode, the electric current can flow in one direction only. Now that we have defined P and N semiconductors and the pi and N junction, we must understand why such a system is sensitive to light. But what is light? In a famous article published in 1905, Albert Einstein introduced the concept of photons as light particles. He was awarded with the Nobel Prize for this work. Light had been extensively studied in previous centuries, and it was concluded that it was made up of electromagnetic waves propagating at a speed c extremely high, about 300,000 kilometers per second. Although this description gave a satisfactory explanation of a large part of the luminous phenomena, could not explain the so-called photoelectric effect, the subject of the Einstein work. The photons are electromagnetic wave packets, and in the following we will treat them just as energy particles. Photon energy is determined by its frequency through the relation E equal h nu, where h is the Planck constant. There is a relationship between photon frequency and colors that our eye perceives. Violet photons have energy higher than red photons. But light is only a small part of the electromagnetic spectrum. Outside of the visible radiation, as the frequency increases, we meet the UV radiation, X-rays and gamma rays. Instead, decreasing the frequency, we find infrared radiation, microwaves and radio waves. Let us now turn to what happens when light and matter interact with each other. An atom can absorb a photon as long as its energy is equal to the energy difference between a filled energy level and an empty level energy level. If this condition is fulfilled, the electron uses the photon energy to jump to the empty level, creating an excited state. The excited electron, after a certain time, can jump back to the original level, emitting a photon. Therefore, absorption and emission of light occurs only at certain frequencies or colors. This phenomenon is responsible for the characteristic spectra of different chemical elements. Decomposing with a prism or a diffraction grating the light emitted or absorbed by different substances, it is possible to understand their atomic composition. Based on what we have said so far about the nature of light and semiconductors, we can understand what happens when they interact. If the photon energy is less than the gap of the material, it will not be absorbed and will continue along its path. The material will appear transparent to this radiation. If the photon has an energy equal to or greater than the gap, it will be absorbed by the materials that will appear opaque to this radiation. An electron will be transferred from the valence band to the conduction band, and the semiconductor shall become a conductor. The absorbed energy can be emitted later in the form of another photon or even dissipated as heat. Now we have all the elements to understand in detail how a photovoltaic cell works. When a photon hits the P semiconductor in the proximity of pi-n junction, an electron will be transferred from the valence to the conduction band and, due to the local electric field, will be attracted by the excess of positive charge in the conduction band of the N semiconductor. Then it will move to the metallic conductor. Simultaneously, the hole created in the valence band of the pi semiconductor will be pushed towards the opposite metal electrode. The generated electrons create a flow of negative charge in the external circuit, going to recombine with the positive charge to the other end of the circuit. In this way, the light absorbed by the photovoltaic cell generates current in the external circuit. This current may be used to power any electric device. Traditional photovoltaic panels based on silicon solar cell have an efficiency of about 15%. This means that only 50% of the solar energy is converted into electrical energy. Why? Is it possible to increase this efficiency? To understand the reasons for this reduced efficiency, we must start from photon energy distribution of solar radiation. It is described by a characteristic function that depends on the temperature of the sun, over 6,000 Celsius degrees. Solar energy is composed by about 5% of ultraviolet radiation, 45% of visible radiation, and the remaining 50% as infrared radiation. In this plot, we see that only part of the solar radiation is absorbed and converted into electrical energy by a crystalline silicon photovoltaic cell. Let's see why. In this slide, on the left, is shown the distribution of the photons flow coming from the sun. On the right, we draw an hydraulic system that mimics the behavior of a solar cell. The various colored tanks put at different heights reproduce the amount of photons coming from the sun. The bigger the tank, the more photons are available. The higher is the tank position, the larger is its energy content. The two gray tanks on the right side represent the pi-n junction. The first highest tank represents the pi semiconductor, while the lowest one represents the n semiconductor. The flow of solar photons is collected from the p tank, but the energy from the tanks on the left is not exploited and corresponds to energy dissipation as heat. So the photons collected by the n tank are transferred to the p tank and fall from the latter, feeding to the turbine that converts only the energy of this latter jump into electrical energy. The higher photons placed in the lowest tank on the left can feed the pi tank, so it will not be exploited. This is the reason why only a part of the solar energy is converted into electrical energy. If the height of the gray pi and n tanks were higher, as using an higher gap semiconductor, the energy of the collected photons would be better exploited, but would collect less photons. On the contrary, moving the two tanks further down, we would collect more photons, but their energy would not be efficiently exploited. Therefore, this is an optimal height of the gray tanks corresponding to the optimal band gap, which allows to obtain the highest possible efficiency for a single junction solar cell. This optimal value is about 1 electron volt, very close to the silicon band gap. The theoretical best efficiency for a single junction solar cell should be about 35% if the other energy losses could be avoided. One way to increase the efficiency limits of solar cells consists by employing a combination of different semiconductor materials with different gap, able to absorb photons from different regions of the solar spectrum, exploiting them in an optimal way. For example, with triple junction cells, efficiency higher than 40% can be obtained. Unfortunately, these cells are very expensive and are generally used in concentration systems where large parabolic mirrors focalize the solar radiation on small-sized cells. How do triple junction cells work? Following the hydraulic scheme previously mentioned, we can see how we can better utilize solar photons, converting a greater amount of solar energy into electrical energy by using 3 pairs of tanks placed at different heights, each of which is connected to a turbine. Many research groups worldwide are working on cell and photovoltaic devices other than silicon. We list some of them here: inorganic semiconductors other than silicon, organic and polymeric solar cells, dye-sensitized solar cells, perovskite-based solar cells, luminescent solar concentrators, and photovoltaic concentrators. This diagram shows the evolution of the efficiency of various types of cells. At the top we find quadruple junction cells, in an intermediate position new generation of silicon cells, and at the bottom organic, polymeric and quantum dots solar cells. Silicon-based photovoltaic cells are the most widespread solar cells on the market. The reasons reside in the peculiar properties that make silicon the ideal semiconductor material for this application. Their cost dropped dramatically in the last years, also for the introduction of new production technologies. Main advantages of silicon are large availability, optimal band gap, 1.1 electron volt for a single junction photovoltaic cell, stability, and currently low cost. The reasons to seek alternatives to silicon resides in making photovoltaic cells with properties that silicon does not have, such as transparency, lightness, flexibility, variety of colors. ENI is carrying on research in these new areas. In particular, ENI is developing flexible solar cells made of plastic materials at low cost, and luminescent solar concentrators that allow to realize transparent photovoltaic panels in various colors. The first project is focused on organic solar cells and the polymer OPV that deliver low-cost solar cells, light and flexible. They can be easily realized developing photoactive inks, and the cells can be printed on flexible plastic substrates. The possible applications of OPV cells are those in which flexibility and the lightness are required characteristics, charging of portable devices, tents, solar sails, and so on. The luminescent solar concentrators are based on sheets of transparent plastic material, including tiny amounts of fluorescent dyes. They absorb part of the solar light, and the emitted radiation is trapped inside the slab and guided, as in an optical fiber, toward the edges where they are concentrated on small-sized solar cells. In this way, you can get transparent colored solar panels. In November 2012, a photovoltaic shelter for charging electric bicycles and based on this technology has been installed in an ENI site in Rome. Among the possible luminescent solar concentrator applications, we can mention the field of building integrated photovoltaics, greenhouses, and noise barriers. We can conclude remarking that silicon-based solar cells shall remain the main photovoltaic product on the market for many years. They already represent an energy source competitive with fossil fuels. Alternative solutions can be useful for applications requiring specific features difficult to obtain using silicon-based solar cells: lightness, flexibility, transparency, color. OPV can be considered good alternatives for flexible devices if some technical and economical issues concerning encapsulating materials and transparent electrodes will be solved. Luminescent solar concentrator technology can be considered a promising solution to fabricate semi-transparent windows or colored photovoltaic panels for building integrated photovoltaics, almost ready for the market. Luminescent solar concentrators represent a bridge between traditional photovoltaic cells and innovative optoelectronics device. Thank you for your attention.